Okay, so to show a bit of insight into how to do the questions of derivatives of inverse trig functions, let's go through some worked examples. This video will go through 3. So the first example is the derivative of inverse tan 2x on 3, and we've got the generic rule there established in the previous video. Firstly, it's important to identify a, so it's based on x over a, and we've actually got 2/3 times x, so that'd be the same as x over 3 on 2. So a is 3 over 2. And so we go and use the formula. So for a we have 3 on 2 over a squared, which is 9 on 4, plus x squared. So you use your usual deft work with fractions, and so simplifying all this now, so we've got 3 over 2 outside of 9 on 4 plus x squared, which comes out as 3 over 9 over 2 plus 2x squared. If we multiply them top and bottom by 2, it gets rid of that denominator of 2 on the denominator. And we have 9 plus 4x squared on the bottom. So 6 over 9 plus 4x squared. Okay, the next question, we're going to have to use the chain rule. We've got y equals e to the inverse sine of x, so it's a function of a function, and I've just written down there in light green the derivative of inverse sine of, that should be an x there, whoops, okay, is 1 over the square root of 1 minus x squared from our previous work. So let u equal inverse sine of x, make a substitution. Du dx would be 1 over square root of 1 minus x squared. Dy du is e to the u, because we've got y equals e to the u once we make the substitution, and we take the derivative of that. The derivative of e to the u is e to the u. And putting it in the chain rule, we have dy du, which is e to the u, times du dx, which is 1 over 1 minus x squared. And subbing back in terms of x, so we have e to the u over the square root of 1 minus x squared, but if we substitute back in terms of x, we would have e to the inverse sine of x over square root of 1 minus x squared. Okay, so the answer is e to the inverse sine of x over the square root of 1 minus x squared. Third and final example, something a little bit different. We're given a function for inverse cos 3x, and we've got to find the maximal domain of the function. Then we've got to find the range of the function, correspondingly find the derivative of the function, and state the domain for which the derivative exists. Now, from all of our previous work, and we've worked very hard on this, we know that in general, for y equals inverse cos of x, we know that the domain of x is the same as the range for y equals cos x. So the domain for inverse cos is from a -1 to 1 inclusive. And what we have here in part A, just change colours, we have part A, part 1, we have 3x is an element of the set, negative 1 to 1 inclusive. So that would mean that x would be the element of the set negative 1/3 up to 1/3. Okay, and that's the maximal domain of the function f. Now going over into our thinking corner again in the lighter green, we know that the range for generic inverse cos of x is from 0 to pi. Okay, so we need to think about the effect that the 4 on the front has, because that's based on 1 inverse cos. Now it'll actually increase all the y values by a factor of 4. So for y equals 4 inverse cos 3x, we have y, it's not equals, is an element of 0 through to 4 pi. So there's the range corresponding to the maximal domain. So now to find in part B the derivative, and so we're going to have to use a chain rule again. So a substitution, u equals 3x, and we can easily calculate du dx as 3. At this stage now, y equals 4 inverse cos of u, and we know that would be 4 times negative 1 over the square root of 1 minus u squared. And I guess I better label that properly. That's dy du, isn't it? The derivative, so dy du. So in the end, we've got to find dy dx. So here's where the chain rule kicks in. It's dy du times du dx. And that's negative 4 over square root of 1 minus u squared times 3. And we also want to substitute back in terms of x. So we have over the square root of 1 minus. Now, u was equal to 3x, so it's 9x squared. Last thing we need to do now is find the domain for which the derivative exists. That's all about the x. So the domain for dy dx. So what we need to look at is, it is all about the denominator, and it's all about making sure that denominator stays greater than 0. Well, in fact, that's not accurate. It's all about what's under the square root sign staying greater than 0, because if it is 0, we've got negative 12 divided by 0, and if it's less than 0, we have the square root of a negative number which has no real roots, no real solutions. So in essence, we have the important statement is we must have 1 minus x squared greater than 0. So we add 9x squared to both sides. So 1 must be greater than 9x squared, and divide both sides by 9, and 1/9 must be greater than x squared. Thus, x must be greater than negative 1/3. Okay, for example, if it was negative 1/4, it would make a true statement. So x must be greater than negative 1/4. If it was less than negative 1/4, say negative 1, you'd be saying something like that, which is not true. Okay, the other condition is that x must be less than positive a third. So that means the domain, more specifically, is exclusive. Excuse me, hope I didn't startle anyone there. So the domain, I should say x is an element of the set there, and the x is an element of the set from negative a third up to a third, but that excludes those values of negative a third and a third.